Hi, this is Professor David Farina, and in today's lecture we're going to be talking about the Copernican revolution, specifically Newton's laws, and a bonus, Einstein's relativity. So, with Isaac Newton came a brand new era of science. Before Isaac Newton, we did not have the mathematical tools necessary to describe the motion of everyday objects. We simply could make observations. And it was actually none other than Galileo who was the first to start making these observations. As we discussed in our last lecture, Galileo was effectively the first real scientist. He used the scientific method to make observations of things that were up in outer space, but he also made observations of things right here on Earth. One of his most famous experiments is, of course, the dropping of various different spheres, and most famously from the Leaning Tower of Pisa in his native country of Italy. And he was capable of timing these experiments as he dropped these spheres, balls, from various different heights, and he was able to determine that acceleration of a body would change over time. In other words, there was an acceleration due to gravity. And that these are what we call like vector quantities. These are going to have both a magnitude and a direction. As opposed to a scalar value that has simply a magnitude, vector quantities have direction also. And that's key to describing how forces and other things like this work. So, some various different cases for acceleration. So, acceleration in the conventional sense, like the increasing of speed, but also deceleration. Decreasing speed is a negative acceleration. It's simply a negative sign in front of the acceleration. Or the change of direction. This is the third way that we can cause an acceleration. So imagine an automobile. There are three main ways that you change your velocity. You can hit the gas pedal, you can hit the brakes, and you can steer the car with a steering wheel. All three of these are changes. And those changes, because we're talking about a vector quantity, even if you're going the same speed, let's say 60 miles per hour, if you're turning, you're actually accelerating. And that's why you feel forces being applied on your body. Now, Galileo's famous experiment from the Leaning Tower of Pisa was actually repeated on the moon. In one of the early Apollo missions, they actually dropped a hammer and a feather, and because the moon does not have an atmosphere, these two objects, when dropped, they were able to hit the ground at the exact same time. So this is a really important check on the ideas of Galileo, which Galileo basically stated that air resistance would be the only reason why you would not see these two bodies going at the same exact rate. And it would have been a major problem for Galileo in his time. So acceleration due to gravity is independent of the mass or weight of the falling object. Now, to be careful here in how we're using these words, Galileo did not have a grasp on the acceleration due to gravity, because gravity had yet to be invented. He was simply making observations. It will not be until our next guy, Isaac Newton, till we have the word gravity to work with and the ideas and mathematics that go along with it. So here's his experiment with an iron ball and a wooden ball. Now, Isaac Newton, 1643 to 1727. If you look back to the times of Galileo, he was living just before Isaac Newton. And then Isaac Newton was born right after Galileo passed away, within a year. Isaac Newton picked up on many of the ideas of both Galileo as well as Kepler. And he's adding to what many of these giants in the world of physics have already done for him. Not to downplay Isaac Newton's role, but he was in the right place at the right time. He had all of the necessary data to make these breakthroughs, and he was the right person to do it. His understanding of mathematics was virtually untouched compared to even people today. He invented or co-invented calculus with Leibniz, and he basically made modern physics. His major accomplishments: invented calculus as a necessary tool to solve mathematical problems related to motion. Discovered the 3 laws of motion. Discovered the universal law of mutual gravitation. So what are his 3 laws? The first of Newton's laws is that an object at rest stays at rest, and an object in motion stays in motion unless it's acted on by some sort of outside force. So they showed an astronaut here. Imagine you're an astronaut, you're floating through outer space. As long as you had an initial push, you would continue in that exact direction forever. And unless something else affected you, some other gravitational pull, you would keep going in a straight line. And since there's very little friction or no friction in outer space, you would just keep going at that velocity in that direction forever. The second of Newton's laws: the acceleration of a body is inversely proportional to its mass, directly proportional to the net force, F, and the same direction as the net force. So what does this mean? Okay, let's break this down. So first off, a force is applied. So they show this person's hand. You're applying a force. Okay. The mass of the object, the heavier it is, it says, the harder it is to push. That's a no-brainer. And the acceleration will also be smaller if the mass is higher, unless your force is equivalently large to make a larger mass move at that same rate. So we get this intuitively. It's part of our everyday lives, but Newton put it in mathematical terms. Newton's third law: to every action, there is an equal and opposite reaction. This boy is stepping off of a skateboard. As he steps off the skateboard, his back leg pushes off the skateboard and it goes flying backward. Even though he's trying to move forward, the skateboard goes backward, he goes forward, and we have equal and opposite reactions. Force applied to force. And here's Newton's laws explained in like 3 different ways. So A, here we've got an object at rest staying at rest. B, object in motion stays in motion in a straight line, unless it's C, acted on by some sort of outside force represented by the green arrow, which causes it to be deflected, and it will continue in that straight line now forever unless acted on by an outside force. Now for this we have to neglect friction, and of course there needs to not be an end of the table because it'll just fall off the table. So this boy's throwing a baseball, and this is proof that gravity is a force. We throw the ball up in the air, and if it were not for a force, this ball would continue off in a straight line forever. But because gravity is a force, it pulls the ball down and causes it to curve back towards Earth again. So Newton's ability to connect what he saw in the motions of things that were common in everyday life to motions of things like the moon traveling around the Earth. So like the idea that gravity existed in the first place that's where Isaac Newton really shined, because no one else up until him were able to even fathom this idea. So Newton was absolutely amazing mind. Now, he also came up with this universal mutual gravitation. And what this has to do with is when we're discussing two separate objects that are separated by some distance, r squared, the r being a radius. So we've got the universal gravitational force, which is G. We've got mass 1, m, and mass 2, which is m2, and they're both over the radius squared. Now, G is the universal constant of gravity. So when we're calculating these, what we're basically saying is that if the masses are greater, there's going to be more gravity. It's in the numerator. This is a constant. And if the radius, because it's in the denominator, if the radius is bigger than the amount of force, F, is going to be smaller. In other words, if I separate two bodies, two planets, for instance, the Earth and the Sun, the Earth and the Moon, if I separate them by a greater distance, their effect of each of their own individual gravities is going to be less than it would be if they were closer, which just makes sense. Now, what also is interesting to point out here is because r is squared, what happens when you take 2 squared? So if I double the radius, 2 squared is 4. So we end up with 1/4 of the amount of gravitational force than we would if we had them one radius apart. If I have 3 times the radius, 3 squared is 9, so you end up with 1/9. Okay? If you have 4 radii away, you have 4 squared, or 16, or 1/16 the amount of gravity. So you can see how this would work. It drops off very, very quickly, as this graph shows. As the amount of distance increases, because r is squared, it creates a very, very fast drop-off in gravity's ability to have this attractive force. And this is effectively how the Sun is able to keep the Earth in orbit. If the Sun did not have gravity, then the Earth would just travel in a straight line. But because the Sun does have gravity, the Earth is in motion. It's trying to go in a straight line, but then the Sun is tugging on it with its gravity, pulling it into this resultant path. Okay, so the resultant path, or net path, is the new vector, the new magnitude and direction that the Earth will be in. And the Sun does this everywhere at all times. So it puts it into a nice curved shape, an orbit. Now, you might think that the Sun is the center of our solar system, but in fact, the center of any gravitational system has to do with the masses of each object. If we had equal masses, well then there would be a center of mass actually between the two objects, which means the objects are going to orbit around that center of mass. If you've got one mass, like the Sun, that's more massive, then the center of mass is going to be closer to that object. And the unequal masses cause the smaller mass to be farther away. Now, what this looks like in terms of orbits and Kepler's laws is that we've got 2 ellipses. If we've got an equal mass, then we've got one ellipse and a separate equally sized ellipse, and they're orbiting a common focus point. And if we have an unequal mass, notice we've got a larger mass here, this focus point, and we've got a smaller mass and its focus point. Notice how the smaller one is closer at some points, and here it's over here. I'm sorry, this is the other way around. I'm looking at this funny. So this is the 2 mass units. This is the one that's more massive, and this is the one that's least massive, or less massive. And this is going to have a bigger orbit farther away. And this one's going to have a closer orbit to that common center of mass, just like this previous diagram. More mass, less mass, less mass. So we can consider the orbital motion as these vector quantities. So if we've got a force that's being applied here, the moon trying to go around the Earth has this vector quantity. It's trying to get away. But the Earth is pulling it back in with its gravity, which causes it to have a new vector quantity. This change of direction, just like the steering wheel on a car, is an acceleration. So when we talk about gravity, we're really talking about an acceleration due to gravity. So how does this connect with our modern understanding? We're going to start talking about orbital motion. Satellite technology can use this property. And Newton actually considered this. Newton came up with something called Newton's cannon. And he imagined a kind of a thought experiment. Well, what if I could shoot a cannon? And if that cannonball could go fast enough, could I get it to leave the Earth? And so he thought about this. And he said, well, objects that are too slow, that are falling back to Earth, are simply going too slowly. And they come down at some distance. The faster you shoot it, the farther it goes. If I could shoot it fast enough, it would go straight out and it would fall at basically the same rate as the Earth curvature occurs. In other words, an orbit. Now, if you launch it too quickly, you can actually set up a scenario where it is in what's called an escape velocity. And there are two main types. There's a hyperbolic orbit and there's a parabolic orbit, both of which are escape velocities in which the object will not return. Now, we can have ellipses that are shallow ellipses that are in very low Earth orbits. You can have circular orbits, and you can even have larger elliptical orbits that are much farther out. So these are three orbit types that we could potentially have. There's also another type called a geosynchronous orbit. With a geosynchronous orbit, we have a specific orbital time period that is equal to the orbital period of the Earth's rotation, which is about 24 hours. And with this, we are able to have communication satellites, like maybe television satellites, where you can put a dish on top of your house and you can send signals back and forth between the dish and a satellite above to play your favorite television show. And so what happens here is effectively the satellite is always in one place in your sky. And so as the Earth turns, as this diagram shows here, notice the continents are in motion because the Earth is turning once per day. The satellite simply matches that same turning rate or period. Now, Newton actually took Kepler's laws and he explained them even further with gravity as part of them. So rather than just describing Newton's third law with the period squared times the distance, the semi-major axis, a cubed, Newton went one step further and said that the balancing force here, called the centripetal force, is what's necessary to keep the object in this like circular motion or the elliptical motion with this gravitational force. So here's the Newton's attempt to try to describe why Kepler's laws work the way they do. Now, tides on Earth, like as in ocean tides, are also a result of gravity. And most of the tides are caused by our Earth's moon. Some of them are caused by the sun as well. And the moon tides are kind of an interesting thing. So first off, we've got these little red arrows here. And we've got a difference of the amount of attraction that the moon has on the water on one side of the Earth compared to the other. And so we end up with these two bulges. So we've got a bulge that faces the moon. That one makes a lot of sense, right? Because the water is closer to the moon, it's going to pull towards the moon. But then a lot of people have a hard time understanding this one. This bulge is produced by the fact that the Earth is also pulled in this direction, and this is the farthest thing away from the moon, and so it's a bulge that's left behind by a lack of gravity. Here we've got a medium amount, and here we've got a lot. So this gets pulled further, this one gets pulled a little bit, and this one gets pulled not so much. And we end up with two bulges of the tides. Now, what people also may know by going to the beach, you might know that there are generally 2 tides per day, and here they are. And they're about 12 hours apart or so. Now, what's actually happening here is the Earth, remember, it spins on its axis. And so as the Earth spins on its axis, we are literally spinning through these tides. Kind of like a bike tire moving through the 2 brake pads. And just like those brake pads, the oceans are actually causing a little bit of friction on the Earth itself, and the Earth is slowing down in its rotation over time. In other words, many billions of years ago, the Earth was actually spinning faster than it is today, and the moon and its tides are actually slowing the Earth down like the calipers on a brake, like a bike tire brake. And as it slows the Earth down, the Earth's day is getting longer. So the next time you say, I wish there were more than 24 hours in one day, just wait a few billion years, and you will have a longer than 24-hour long day. Now, the forces are all balanced out at the center of the Earth, but excess gravity pulls the water towards the moon on the near side, and excess centrifugal force pushes the water away on the far side. So that's the basic explanation of why there are 2 tidal maxima each day in a 12-hour cycle. Now, there are some special tides, and that has to do with the orientation of both the sun and the moon. So during the spring tides, we have a tidal bulge that is at its maximum extent. In other words, on these particular days, we've got the lowest low tide possible and the highest high tides possible. And this is due to the orientation of the full moon or the new moon with the sun. And so we create a straight line between moon, Earth, and sun at full moon, or Earth, moon, and sun at the new moon. And this creates a tide where we combine the forces by the moon and sun together to make a single tide. Now, if we go 2 weeks ahead, 1 week ahead from either of these, at the either first quarter moon or the third quarter moon, you'll now see that there's a 90-degree angle between the sun, Earth, and moon, or the sun, Earth, and moon. And as a result of this, you get a moon tide in one direction, and then we get a sun tide in the opposite direction. And this no longer creates that largest difference in tides per day. It produces the least difference in tides per day, called a neap tide. Now, when you're talking neap versus spring tides, these are noticeable differences that people have recorded for thousands of years. It was known about by Isaac Newton and was one of the main reasons that he was able to connect the dots between gravity and what happens here on Earth. Now, one thing that's kind of interesting to think about also is that the Earth's rotation can also play a role in the way in which the tidal bulge gets pushed forward slightly by the Earth's rotation. What this ends up doing is it creates a net force on the moon in this direction that points towards that bulge, which causes the moon to accelerate faster, which means the moon's orbit is actually getting bigger. The moon is speeding up, its orbit is getting bigger, and it does so with the rotational velocity of the Earth. So, in other words, the Earth loses its speed and the moon gains it. We're transferring energy via gravity. And there are some of the vector forces involved. This is the net force. It's pulling it in this direction a little bit faster. In comes Einstein. So Isaac Newton, of course, most of his theories, his laws, I should say, are capable of explaining everything we need to know in order to do most space flight. We can land spacecraft on the surface of another planet with mostly Newton's laws. But in certain situations, Newton's laws didn't work. And Albert Einstein, in the early 1900s, started to come up with some ideas to help to explain these very unique situations where things were moving very fast, like near close to the speed of light. And his theory, his first step into this theory was his theory of special relativity. He also revised some of our understanding in gravity, and then he came up with the theory of general relativity. Now, it's something notable to say that Albert Einstein is actually better known for some of his other work, but his work when it came to gravity and his work that came about as a result of special relativity and general relativity is all we're going to be talking about today. Some of his work on light and optics allowed us to have things like lasers today. So much of his work is also very interesting and important. So two main postulates, ideas that help us to understand special relativity is that if you were in a spacecraft looking out, if you were moving at a constant rate, you might not even know that you were moving. In other words, the only thing that allows you to know that you're in motion is an acceleration, turning, speeding up, or slowing down. If you were at a constant rate of motion and we had a smooth sailing like you would in outer space, it wouldn't feel like anything at all. And so that's an interesting observation. Gravity and an acceleration feel the same. This is the equivalence theory. It says that the laws of physics are the same for all observers, no matter what their motion, as long as they're not being accelerated. The second postulate, the velocity of light, c, is constant. It'll be the same for all observers. So that means even if you're moving at nearly the speed of light, if you saw a light beam, it would also be going the speed of light. Even though you're going in the same direction, if you shot a laser beam, it would leave you at the speed of light. Excuse me. General relativity. So in general relativity, we've got now a person sitting on a launch pad, and he says, I feel gravity. I must be on the surface of a planet. Yet when he's in outer space, if we apply the correct amount of thrust, and if we had a perfectly made rocket that you felt no vibration from, he may still think he's sitting on the launch pad if we provide an equal amount of acceleration. Some of the other cool effects due to Einstein's theories is gravitational lensing, the bending of light. In fact, we've observed this, and it was one of the key things that helped to support Einstein's theories early on. He estimated that if you had some background stars way back out here, if their light was passing close by to the sun, the light would actually curve around the sun and make it appear to be at a different place than it should be. The best time to view this is during a total solar eclipse. And so early eclipse methods were able to detect the deflection that Einstein predicted to many decimal places, confirming his theory and providing him almost international fame. So what does this mean? It means that space and time are curved around gravitational bodies. Imagine that now. It's almost like a fabric. Imagine it like a trampoline, and you place a heavy mass in the trampoline, it's going to sag. That's effectively what's happening to space and time as we place a gravitational source, a planet or a star or a black hole, into that. It will curve space and time around it. Something I wanted to throw in here is something called a zero-G flight. These flights are something that allow movies like Apollo 13 or some of your favorite Hollywood movies to be possible. It's also a way we train astronauts for the rigors of space flight. A zero-G flight is done by taking a large aircraft like a 747, for instance, and flying it nearly straight up in the air, 45 degree angle. And we're flying it so high at that rate, we're going to be going at about twice the G-forces. You're going to feel twice as heavy as you are. But as you start going back down, we take it at 20 degree nose low position, and we're going to drop down at the exact same rate as you would free fall. And these are people in free fall now. They feel weightless. It's just like you would be in outer space. And so this allows, as I said, astronauts to train, but it also is something that, is done for movies. And I think you can even get in here and pay to take a zero-G flight. It might be pretty cool to do. And another cool thing that this gravitational lensing can do is it can bend light from very large objects like galaxy clusters, for instance. And it allows us to see back in the earliest times of the universe. Because remember, as we look back in time, we're actually looking, as we look back in deeper into space, we're actually looking back in time. So we're able to see things from the very early universe. These are little gravitationally lensed galaxies that live somewhere behind that galaxy cluster. And just like light coming around the sun, the bending of the light around those galaxy clusters are going to allow us to see things that are behind them. Another important early observation of Einstein's general relativity was done watching the orbit of the planet Mercury. So it advances in its what's called perihelion, its closest to the sun point, over time. And it wasn't quite understood how this worked, and Einstein's theories were necessary to understand these things fully. Finally, another effect of general relativity is the warping of time. So something called time dilation. As you get closer towards a gravitational source, like this black hole here, time is actually going to be stretched, and so will light rays. So if light left as, let's say, a visible light beam, it would get stretched or red shifted more and more towards the radio side of the spectrum. So gravitational redshift is an important property of gravity. And here's a quick historical overview of these people who lived at various different times, other things that were going on. So just pause the video for a moment and check this out. I really like this slide a lot. And if you look here, the 99 years of astronomy, we had Galileo, Tycho Brahe, Kepler. Other people around at the same time were Shakespeare, Elizabeth I, and Rembrandt. William Penn from Pennsylvania, here his time period was at the same time as Isaac Newton. All right, people like George Washington. So you get a hope, and here's Copernicus. So you get a really good understanding of kind of where these people were in time and what was going on in the world. Thank you, everybody, for watching the video. I hope you enjoyed Chapter 1. I really hope that the additional information here was helpful for you and interesting. Have a great rest of your evening.